Hello.
Yes, sir.
Okay, all right. So let me start recording. Is slides visible to you?
Yes, sir, visible.
Okay, all right. So so just quick recap of what we have done in the last class. In the last class, we started looking at the evaporators. What we said in the evaporator is evaporators are extremely important heat transfer equipments because most of the food processing operations are primarily done using the evaporators. Okay, and if you look at the amount of food processing uh, uh, the fraction of food processing operations in the in the commercial operations of any country, that is significant. Okay, so in that sense evaporation is one of the very important process operation. Okay, all right. Again, if you look at the evaporators, these are primarily used in paper industry, food industry, production of salt and sugar, etc., isn't it? So it's an extremely important operation. So we started looking at different types of evaporators. We have seen different types of evaporators. Then we said that primarily three quantities are important, two quantities are important: capacity and steam economy. So capacity is the amount of vapor produced per unit time, that is the capacity, whereas steam economy is how much steam you are using for producing a per kg of water vapor. Okay, so that ratio is called as a steam economy. So typically if you are using a single effect evaporator, that means only one evaporator unit is used, then the steam economy is less than or approaching to 1. So clearly steam is incurring the cost. Very often we are interested in having more vaporization for the given amount of steam. So in order to improve the steam economy, there are different ways of doing it. The first one is the use of preheaters. So you are heating the feed using the outlet vapor coming out from the evaporator. So by doing that, you are in a way improve the steam economy. But very often the methodology used is a multiple effect evaporator and vapor recompression. So in multiple effect evaporator, what we do, the multiple evaporator units are arranged one after another in a series, isn't it? And the vapor from the previous unit is used as a steam to the next unit by using the vacuum. So that's what is used in multiple effect evaporator. In a vapor recompression, the vapor coming out from the evaporator itself is compressed, and by compressing it, its enthalpy is increased. And with the increase in the enthalpy and the boiling point temperature, the same vapor can be used as a steam. Okay, so unlike the multiple effect evaporator where multiple units are used one after another, in a vapor recompression we use only a single unit, but the vapor coming out from the evaporator itself is compressed so that it can become a steam. Okay, so these are the slight difference. So then we have looked at multiple effect evaporator. We looked at different feed combinations: forward feed, backward feed, parallel feed, etc. Also we have discussed vapor recompression. In vapor recompression there are two types. One is the thermal recompression and mechanical recompression. So thermal recompression is using the steam jet ejector if you are having a high pressure steam available. In mechanical recompression, a compressor is used for compressing the vapor. So then we started looking at the design of evaporator, and I said in the last class that this part we are going to look at again in more detail. So in a design of evaporator, why we are looking at design of evaporator, because if you join a process industry, you will have to design the evaporator. You need to find out how many number of effects you wanted to use in your process, how the cost dynamics coming into the picture, that everything you will have to design, isn't it? So this part we wanted to do it little bit in more detail. Okay, so the first step in the design of evaporator is first you make a schematic diagram the way I have made, and then denote the different variables here. Okay, and once you denote these variables and the contacting pattern, so in this case the forward feed is there, so feed is going from this direction. But let's say if you would have been the backward feed, the feed would have gone from this reverse direction here. Okay, so depending on the contacting, then you make the energy balance. So here in this forward feed case, the energy balance is shown. So energy balance, one has to make the energy balance at each of these stages. Effect 1, effect 2 and effect 3. So for effect 1, the energy balance is given here, WFIF plus WSIS. So this is nothing but what? WFIF is nothing but whatever the feed coming in multiplied by its enthalpy. So that is the total amount of energy coming in into the effect 1. WSIS is the steam coming in and its corresponding enthalpy is IS. So this is the energy coming in through a steam. Then outlet here are WF, WS1, WF minus WS1 is the outlet stream, product stream, multiplied by its enthalpy is nothing but the energy going out with the product. Also, there is a vaporization taking place. So WS1 into IS1 will be the energy going out with the vapor. Also, the steam is getting condensed here. So WS into IL will be the energy going out with the condensate. But this equation can be further simplified if you assume that the steam is a saturated steam. Okay, so if you assume the steam is a saturated steam, this WS1, if you assume that it's a saturated vapor, with that assumption, this entire equation gets simplified significantly. So that's what we have seen here. So WF, I have this term remain as it is, but you can see that the second term, WSIS, instead of IS, we are multiplying a latent heat of steam. Okay, because we are assuming that this steam is a saturated steam. So WF plus IF plus WS lambda S, this is the energy coming in. When we are using the saturated steam, then we don't need to consider this WSIL because there is no sensible heat, isn't it? So the temperature of this condensate and the temperature of this steam both are same, isn't it? So we don't need to consider this WSIL in case of using the saturated steam. So that's what we have omitted here. So right hand side will be again WF minus WS1 I1 plus WS1 IS1. Similarly, for the second and third effect, we can write down the balance equations as it is. So the only change in that case will be whatever is the input that is multiplied to the enthalpy. For instance, in the second effect, the input feed is going to be what? WF minus WS1. So WF minus WS1 into I1 will be the input here, plus WS1 lambda S1, because this vapor coming out from the first effect is acting as a steam to the second. So WS1 lambda S1 will be the heat input here. And the right hand side will be WF minus WS1 minus WS2. That is what is going out from the second effect multiplied by I2 plus WS2 into IS2. And similarly, we can write down the balance equation for the third effect. Also, these are nothing but the energy balance. But in addition to that, there will be a heat transfer equation. So remember, in the first effect, the heat is supplied by the condensing steam here. So this condensing steam, which is having a flow rate of WS. So WS into lambda S will be the amount of heat transferred to the first effect, isn't it? And that should be given by what? Heat transfer, total amount of heat transfer. So total amount of heat transfer is what in this case? Area of this first effect multiplied by overall heat transfer coefficient of this first effect multiplied by delta T. So that is what we have written here, U1 A1 delta T. So delta T will be what? Temperature of the steam minus TB1. So UA delta T1 will be the heat transfer to the first effect, and that should be given as WS lambda S. Similarly, for the second effect, it will be WS1 lambda S1 will be given as U2 A2 delta T2, and for the third effect, it will be WS2 into lambda S2 is given as U3 A3 delta T3. And note that here delta T2 is what? Delta T2 is TW1 minus TB2. Whereas this TW1 and this TB1 both are same if the solution is dilute. That means there is no boiling point elevation. So this T1 and this T1 and this this T1 and this TB1 are same if there is no boiling point elevation. But if there is a boiling point elevation, that means the solution is concentrated. In that case, this TB1 will be higher than this T1. Okay. So this T1 is a temperature of a pure solvent, whereas this TB1 is the boiling point temperature when the solution is having a solute. And clearly, whenever there is a solute, there is a boiling point elevation. And therefore, this TB1 and this T1 will not be same if the solution here is concentrated. Okay. So these are the three energy balance heat transfer equations. Again, from this heat transfer equation, one can find out the area, back calculate the area. So area A1 here will be what? Ws lambda S divided by U1 delta T1. Similarly, you can calculate A2 and A3. Okay. Now, this is what we have seen in the last class. The most important part to note down in the evaporator is, if I am the manufacturer of the evaporator and I wanted to design the multiple effect evaporator, what I will do? I will make the same unit, because if I make a different sized unit in a multiple effect evaporator, then I require a lot of cost, because I need to set up my production line in such that I will get two different size equipments, and that is going to incur a cost, isn't it? So the best operating practice is to use the same size of equipment one after another repeatedly, instead of having. So what I'm trying to say is the size of effect 1 and size of effect 2 and size of effect 3, all three effects will have a same size. In fact, these three units are same sized unit. You will not be able to distinguish between them. You are only putting them one after another and then calling them as a effect 1, effect 2 and effect 3. It's not that the size of effect 2 is lower than effect 1 or size of effect 3 is lower than effect 2 or 1. It's not like that. They are of same size. Why? Because you require a same production line. Only one production line you require if you do like this. Otherwise, you require 3 production lines. That is going to incur a cost. So the best operational practice is to use the same unit repeatedly one after another instead of having a different sized unit. Is it clear, Utkarsh? Make sense? Hello?
Yes, sir.
Another interesting thing is, if I am having a same size unit, means what? They will have the same coiled here, isn't it? Heat transfer coil, correct? So that means what? Their heat transfer area is same. Do you agree?
Yes, sir.
So the heat transfer area of all three units is going to be same. Okay. Now there are 3 steps in designing the evaporator. So first stage is, in the first stage we don't know. So see, typically whenever we are designing the evaporator, what we know is, we know the input temperature TS and we also know the outlet temperature T3 here. T3 or TB3, this is something we know. In between, what is the temperature T1, what is the temperature T2, we don't know. It depends on how much heat transfer is taking place in individual units. We know the same heat transfer area is there in all 3 units, but that doesn't mean that the heat transfer will be same. But in order to solve this problem, there is a trial and error required in this. But in order to solve this problem, the first step is to assume that, this word is very important. First step is to assume that the heat transfer in effect 1, effect 2 and effect 3 is same. Of course, it is not same. We will revisit this assumption again. But to start, we are making this assumption. We are making this assumption that the heat transfer in effect 1, effect 2 and effect 3 is same. So if we make that assumption, then we can equate this equation. U1 A1 delta T1 U2 is equals to U2 A2 delta T2, and that is equals to U3 A3 delta T3, isn't it? Because this first term is the heat transfer in the unit 1, second term is the heat transfer in the unit 2, and third term is the heat transfer in unit 3, isn't it? This is the assumption. We will revisit this assumption again. That's where these iterations are coming into the picture. Again, area 1, A1, A2, A3 are same. So we will get U1 delta T1 equals to U2 delta T2 equals to U3 delta T3. That is what we are going to get. In addition to that, the total temperature difference across this entire setup of these 3 units. What is the total temperature difference? TS minus T3, isn't it? Ts minus T3 or TB3 is the total temperature difference. I am saying TB3 and T3 both are same if I'm using the dilute solution. If I'm using the concentrated solution, in that case this TB3 will be higher than T3. Okay, so the total temperature difference is going to be Ts minus TB3. That is what the total temperature difference, isn't it? Now this total temperature difference we know, and this total and individual temperature difference between this unit and this unit plus this unit and this unit, that summation will be this total temperature difference, isn't it? That's what we can get it here. So total temperature difference delta T will be nothing but what? Delta T1 plus delta T2 plus delta T3, and that should be equals to Ts minus TW3 minus boiling point elevation, isn't it? Correct?
Yes, sir.
So that's what we have seen. Remember here, what is delta Ts minus TB1? This is delta T1 plus TW1 minus TB2, that is delta T2 plus TW2 minus TB3. If we assume that TB1 and TW1, TB1 is same as TW1 and TB2 is same as TW2, in that case, we don't get any boiling point elevation. But if these are not same, then this additional term minus boiling point elevation comes into the picture. Do you agree? Yes or no?
Yes, sir.
Okay, so typically this problem becomes easy if the solution are dilute, because then you can safely ignore this boiling point elevation term. If your solutions are not dilute, these are concentrated, in that case you start with the assumption that the evaporation of the vapor takes place in the all three effect is same. So 1/3, 1/3, 1/3 is occurring in all three stages. And based on that, you can calculate the concentration of the solute in each of these stages. Once you know the concentration of solute in each of these stages, then you can use these equations and calculate the boiling point elevation. That is the way to solve the problem if the boiling point elevation is important in the problem. Otherwise, you neglect the boiling point elevation and you solve. So okay, so from this equation 8 you get U1 delta T1 equals to U2 delta T2, U3 delta T3, and from equation 9 we get delta T1 plus delta T2 plus delta T3 is delta T. By using both these equations, if you rearrange, what we get is the equation number 11. Equation number 11 is given as delta T1 divided by delta T is given as 1 by U1 divided by 1 by U1 plus 1 by U2 plus 1 by U3. So this is a very important equation. Remember this equation. Okay, so one can find out the in-between temperatures using this equation. If I know the terminal temperature Ts and Tw, and I know if I know this U1, U2, U3, I can find out what will be the terminal temperatures. What will be the intermediate temperatures? Intermediate temperatures like Tw1 and Tw2 I can calculate using this equation 11. So the first step is to assume the same heat transfer, calculate this delta T1, delta T2 and delta T3. Once we calculate delta T1, delta T2, delta T3, for instance, if we know delta T1 is what? Ts minus Tw1, isn't it? Ts minus Tb1 or Tw1, that is delta T1, isn't it? So delta T1 we know, we know Ts, we can find out Tb1. Once we know Tb1, we can put that Tb1 in this equation, isn't it? And we can calculate Tb2. We can also calculate Tb3. Once we know Tb1, Tb2, Tb3, these three temperature we know. Remember, in this case, if you assume that the steam is evaporating, vapor is evaporating at a saturated condition here, we can pinpointedly find out what will be the latent heat of vaporization here. What is the latent heat of vaporization here? That we can find out pinpointedly using the steam tables which are given backside of the book. Okay, and we can proceed with the solution. So once we know the delta T1, delta T2, delta T3, we can find out latent heat of vaporization lambda S, lambda S1, lambda S2, etc. And then we can use these balance equations. And we can find out WS1, WS2 and WS. Once we know WS1, WS2 and WS2, WS, WS1, WS2, we can use these heat transfer equations, and we can back calculate area A1, A2, A3. Now remember, we started with the assumption that the areas are same, but after back calculation, the areas, you might not get the areas same, isn't it? So if you don't get the areas same, that means this assumption that your heat transfer in all three effect is same is not correct. So you can revisit this assumption by varying this delta T1 little bit. For instance, if A1 is higher, so you wanted to reduce A1. So you wanted to reduce A1 means you will increase delta T1. So you will rearrange this delta T1, delta T2, delta T3 between the total value of delta T such that your area matches. Once your area matches, that is your final design. So you do the trial and error till your area matches. Okay, once these areas are close to each other, then you calculate the average area and take it for each effect, and delta T values are redistributed in three effect and calculations are repeated till the areas comes out to be the same. That's what I have said. Is it clear? The procedure is clear?
Yes, sir.
So this procedure you will appreciate by looking at the problem itself. Okay, so let's look at two solved examples and then we are done with the syllabus. Okay. So in this problem, what is given? A solution boils at 106 degrees Celsius. So this temperature here, solution boils at 106. So this temperature T1 is given as 106. Okay. Then in a double effect evaporator, so I have shown this double effect evaporator here. Forward feed means the feed product coming from first effect is given as an input as a feed to the next effect. So that is the forward feed. Okay. The rate of vapor generation is 2000 kg per hour and liquor with 15% solute enters the second effect. So the rate of vapor generation is 2000 kg per hour. So here the rate of vapor generation in the first effect is 2000. So WS1 is given as 2000 kg per hour. Okay. And the feed here entering to the second effect is 50% solute. So that I have marked here. Okay. A vacuum of okay, the product leaves the second effect at a temperature of 88 degrees Celsius. So product leaves the second effect. So this product coming out from the second effect at 88 degrees Celsius. So that is also given here. Okay, then a vacuum of 500 mm HG is maintained. So vacuum, this vacuum word is very important. So what the pressure here will be what? 760 minus 500, that will be the total pressure, isn't it? Here in the second effect, correct? 760 is the 1 atmosphere, and if you are vacuum of this 500 mm Hg is set, so this 500 we have to subtract from 760, so that will be the pressure. Okay, now this information is given. Again, what is been given is the preheated feed. So amount of feed entering the first effect is 15,000 kg per hour. And the temperature is 70 degrees Celsius here, but this is after preheating. So what is the input temperature of the feed? What is the inlet temperature of the feed before preheating? That is what the question is asking. So and outlet temperature of this product is given as 40 degrees Celsius. So here 88 degrees Celsius is there, but after exchanging the heat, its temperature is 40 degrees Celsius. But how much is the amount of this product coming out from the second effect, that we don't know. Also, we need to calculate the rate and the concentration of the feed. So we have to calculate what is the concentration of the feed here. That is what we have to calculate. Okay, so problem is clear?
Yes, sir.
Now, all these are the information. These are the information. So T1 we were knowing. This pressure we are knowing. So this T1, so since vapor is coming out here is a saturated vapor. So once we know this temperature for a saturated water vapor, we can find out what will be the latent heat of vaporization. So from these steam tables given at the back side of the book, we can directly obtain this lambda S1 for this temperature. So once we know the saturation temperature is 106, for that the latent heat of vaporization comes out to be 539. That we can directly take from the table's backside. Again, once we know this pressure here, 760 minus 500, for this pressure, we can pinpointedly find out what will be the saturation temperature and its corresponding latent heat of vaporization. So this 73 and 556, this we can find out from the tables given backside just by looking at this temperature T1 and this pressure P2, by assuming that both these are at the saturation temperature. Now this information is known, correct? Now let's make the balance for the second effect. Let's make the balance for the second effect. Okay, so the vapor leaving the first effect is at 106 and 1 atmosphere, so we can get lambda S1 like this. Also the pressure in the second effect is 260 mmHg, so saturation temperature comes around 73, so lambda S2 also we have found out. Now make the balance at the second effect. So second effect, the balance will be what? Wf minus Ws1 into I1 plus this Ws1 into lambda S1, and that should be equals to what? Wf minus Ws1 minus Ws2 into I2 plus Ws2 into lambda S2. That's what is going to be the balance, isn't it? This is what the balance equation. Now this balance equation, we take it at 88 degrees Celsius. So here, remember this enthalpy multiplied. This is the enthalpy multiplied, isn't it? This enthalpy has to be taken at a particular reference temperature. Now let's take the reference temperature 88. Why 88? Because if you take the 88 as a reference temperature, this outlet is at again 88. So this Wf minus Ws1 minus Ws2 into I2 will be what? 0, because I2 will be what? CP/dT. I2 enthalpy is the CP/dT, isn't it? So Cp into delta T. Delta T is what? 88 minus reference temperature. Reference temperature is also 88. So this becomes 0. So in order to get rid of this second term here, we take the reference temperature as 88. Okay. Because here we don't know what is WS2. WS2 we have not calculated. It's not been given here. Remember, WS2 is unknown. So it is better to take the reference temperature as 88. Then this term goes away. And this entire equation do not have a WS2 term. This entire equation will have only one WS2 term here. But this I2 term will not be there. Okay. So this equation gets simplified immensely if we take the reference temperature as 88. Okay. So let's put all the values here. Wf is 15,000 minus Ws1, that is 2,000 into I1. I1 is what? CP/dT. So in this case we are assuming the specific heat of everything is same, isn't it? Water is what we are using, isn't it? So for a water, the Cp value is taken as 1, isn't it? 1 kilocalorie per kg, isn't it? That's what it is it? Right?
Yes, sir.
So that 1 is used here into dt. Delta T is 106 minus 88. So 106 minus this 88, because 88 is the reference temperature. Okay. Plus this 2000 into 539. 2000 into 539, because 2000 is the WS1 into this lambda S1 is 539, and that should be equals to this first term becomes 0 into WS2 into 556. So by back calculating, we get WS2 is equal to 2360. So we have obtained how much is going to be evaporated here. So that comes out to be sorry. That comes out to be 2360. Once we know this 2360, we can put it in the balance equation here. Now WS1 we already know, WS2 we have already calculated. Now we can make the balance here. Remember this WF we already know 15,000, WS1 we have already know 2,000, and WS1 we have now calculated. That comes out to be 2360. Now we can make the balance here at a preheater. So Wf in minus Ws1 minus Ws2 into this 88 is the temperature here, 88 minus 40. That will be the amount of heat transferred by this feed coming out from the second product coming out from the second effect, isn't it? And it is used for preheating the feed. So preheating the feed, which is equals to 15,000 kg per hour. So we can make the balance here. So 15,000 into 70 is the outlet temperature minus T in, and that should be equals to Wf minus Ws1 minus Ws2. This is the total amount of product coming out from the second effect multiplied by CPDT, so 1 into 88 is the outlet temperature of the product coming out from the second effect, and the temperature of the product after exchanging the heat in the preheater is 40 degrees Celsius. That is what is given in the problem. This is the 40 degrees Celsius. So this 88 minus 40, that will be the delta T here. So this WF minus WS1 minus WS2, this is already known. Everything is known in this equation except this Tin. So we can calculate this Tin. Tin comes out to be 36 degrees. So we have obtained this temperature in for this feed here before the preheater comes out to be 36 degrees Celsius. Also in the problem, what is being asked is concentration of the feed. So concentration of the feed we can calculate. So here 15,000 kg per hour solution is given. But here in the second effect, the feed coming out from the second effect is at the 50% solute. So how much is WF minus WS1? WF minus WS1 is 15,000 minus 2,000. That is the WF minus WS1. And its concentration of the solute is 50%. So multiplied by 0.15, that will be the amount of solute present, isn't it? So, and the solute remains the same. Amount of solute is going to be same because it's not going to evaporate, isn't it? So the amount of solute we can calculate, that is 1950 using this, and amount of solute divided by total amount of solution present, that gives the concentration of the feed, isn't it? So amount of solute comes out to be 1950 divided by this 15,000 gives the concentration of the feed, that comes out to be 13%. Is it clear?
Yes, sir.
All right. Let's look at the second problem. So in the second problem, what is been given is an aqueous solution of high molecular weight solute is concentrated from 2% to 35% by weight at the rate of 6. Please go ahead.
Yes, screen is not visible.
My screen is not visible. Okay, let me just share again. Just now or?
Just now, as we started question 2.
Thank you. Is it visible now?
Yes, sir.
Okay. Okay, so example 2. So in this particular, is it visible to everyone? Yes, right? Hello?
Yes, sir.
Okay, thank you. So in the second example, what is given is an aqueous solution of high molecular weight solute is concentrated from 2% to 35% by weight at the rate of 6,000 kg per hour in a forward feed double effect evaporator. As I said, remember every time whenever the evaporator problem is there, or if you wanted to design it, first make a schematic like this. Note everything, whatever is known, and then try to calculate the unknowns. Okay, it becomes easy. Otherwise, you will be lost. For instance, instead of a forward feed, if I ask a question of a backward feed, the equation changes, but you get to know all those equations very easily if you make this figure initially. So make this figure initially, then everything becomes very easy. Okay. So the feed is coming with the concentration of 2% and it is getting concentrated to 35% by weight at the rate of 6,000 kg per hour. So 6,000 kg per hour is the WF coming in. 2% is the initial weight fraction. Okay, and after the concentration, it becomes 35% concentrated. Okay, so 35 concentrated, so solute concentration I can calculate here, isn't it? So 0.02 multiplied by 6,000, that will be the amount of solute present in the solution. So that is 120, and the solute will remain same, isn't it? So now 35% if I am saying here, so 35%, when this 120 becomes 35%, that solution amount I can calculate directly, isn't it? So that comes out to be 120 divided by 0.35 if I do. My final concentrated solution is 343. So if I subtract this 343 from this 6,000, that is the amount of evaporation takes place between both the effects 1 and 2. So 5657 is the amount of steam, amount of vapor evaporated, isn't it? So WS1 plus WS2, that total will be 5657. Is it clear to everyone? Just a pure mass balance, isn't it?
Yes. Yes,
And
sir.
by taking the basis of this solid content is not going to change because it's not going to evaporate. So here the solid content is 2%, but that comes out 120 kg per hour. Here by keeping that 120 constant, I can calculate how much is the total amount of solution. That comes over around 343 kg per hour. If I subtract that from the 6000, that gives me the total amount of evaporation takes place between effect 1 and 2. So that is nothing but WS1 plus WS2. So that is 5657 kg per hour. Okay. Again, what is been given? The dilute feed at 15 degrees Celsius enters the first effect. So temperature here is 50 degrees Celsius. Again, the saturated steam at a absolute pressure. So saturated steam at PS equals to 2 bar is given. So if I know the pressure as 2 bar, I can pinpointedly calculate the saturation temperature. That comes out to be 120 degrees Celsius from the tables given backside of the book. Also corresponding lambda S I can calculate. That corresponding lambda S is nothing but the latent heat of vaporization, that is 2200 kilojoule per kg, isn't it? That I can calculate. WS1, lambda S1, T1, these are unknown here. Again, what is been given? While the absolute pressure of 0.0139 bar is maintained at second effect. So here the pressure is 0.0139 bar. So for this particular pressure, again, I can calculate the saturation temperature, and that saturation temperature is around 12 degrees Celsius. And lambda S2 is 2470. Okay. So again, I am assuming that the boiling point elevation is negligible. So this T1 is taken as TB1 here, and this T2, which is 12 degrees Celsius, I can take as TB2. Of course, that's not a good assumption. Why? Because here the concentration is 35%, but we can still go ahead with that, isn't it? Otherwise, we have to calculate the evaporation. So evaporation taking place here, evaporation taking place here. Then we have to calculate the concentrations at both the places, and then we can calculate the boiling point elevation. Okay, that is also another way of, that will be a more accurate way. But in order to avoid that, a lot of complications, we are assuming that the boiling point elevation is negligible here. Okay, is it all right to everyone?
Yes, sir.
So water is evaporated. So we are taking 4.1 kilojoule per kg per Kelvin as a specific heat of the water. Okay. Now what we have to calculate the evaporator areas and steam economy. That's what we have to calculate. Now here in this case, you can see that this WS we don't know. This WS1 we don't know. WS2 also we don't know. We only know that WS1 plus WS2 comes out to be this 5657. This much we know, isn't it? So now, and the temperature difference we know. So here TS is 120 degrees Celsius. Here T2 is 12. So total temperature difference between these 2 points is nothing but what? 120 minus 12 is what? 120 minus 12 is 108, isn't it? So 108 is the total temperature difference. That much we know. Now let's do the calculations. So remember, what is the first stage? What is the first stage for designing? Start with this equation, isn't it? U1 A1 delta T1, U2 A2 delta T2, U3 A3 delta T3. This should be same. This is the first stage, isn't it? And this first stage with the assumption that the rate of heat transfer is same. Of course, the rate of heat transfer is not same, but just to start, this is what we are assuming. So with this assumption, we get U1 delta T1, U2 delta T2 equals to U3 delta T3. So with this and this total delta T we know, isn't it? So that's what we are trying here. See, so delta T1 plus delta T2, this total delta T we know, that is TS minus T2, 120 minus 12, that is 108 degrees Celsius. Also, if you are assuming the total heat transfer area to be same and the heat transfer to be same, in that case U1 delta T1 equals to U2 delta T2. So here U1 value is already given in the problem. U1 is 2000, sorry, U1 is 2000 and U2 is 1500. So we can put that 2000 delta T1 and 1500 delta T2. And now we are having this equation as one equation, and there is another equation, this delta T1 plus delta T2 equals to 108. So two equations are there, two unknowns are there. We can calculate delta T1, delta T2. Is it clear to everyone? Does it make sense?
Yes, sir.
So from this equation, these two equations, we can calculate delta T1 equals to 46 degrees Celsius and delta T2 equals to 62 degrees Celsius. Now, delta T1 is what? Delta T1 is nothing but Ts minus T1, isn't it? Delta T1 is what? This Ts minus T1 is delta T1 here, correct? So this 120 minus T1 is nothing but 120 minus T1 is nothing but 46 degrees Celsius. This is what we have obtained. So we can back calculate T1. Once we know T1 is 74 degrees Celsius, this T1 we have calculated as a 71 degrees Celsius. Now we can go back to the steam table. So from the steam table, if we take the T1 equals to 74 degrees Celsius as a saturation temperature, what is the value of Y? Lambda S1. So lambda S1 comes out to be, from the tables backside of the book, comes out to be 2330. So lambda S1 we have calculated. Similarly, okay, so now you can, okay, so now you can, similarly you can calculate T2. So T2 will be what? Once we know this T1, 74 degrees Celsius is what we have obtained as T1. Delta T2 is what? Delta T2 is nothing but, T1 minus T2 is delta T2. So T1 we have obtained 74 minus 12 is nothing but 62. We can calculate T2 also. So T2 also, if we calculate T2, T2 comes around, in this case, what will be the value of T2? Can anybody tell me? T2 comes out to be, remember the 62 is nothing but what? 74 minus 12, isn't it? So T2 is already, oh, sorry, T2 is 12 degrees Celsius, isn't it? That's already given. Sorry, I just missed the point. Okay, so this 12 degrees Celsius is already there. So this 2470 we already know at this temperature. Okay, all right. So now in the first effect, let's make the balance, energy balance over the first effect. So the energy balance at the first effect, assuming the T1 as a reference temperature. Why T1 as a reference temperature? Because this second term is going to be 0 if we take T1 as a reference temperature. So our equation gets simplified immensely if you put T1 as a reference temperature. So WF into IF, WF is nothing but what? 6000 into CPDT, CP is 4.1 into delta T is nothing but what? 50 minus reference temperature is T1, T1 is 74. So 50 minus 74 plus Ws into lambda S. Ws is unknown. Lambda S we already know. Lambda S is 2200 and equals to right hand side this Wf minus Ws1 into 0 because I1 will be, CPDT will be 0 because here delta T is 74 minus 74. So that becomes 0. So this entire term becomes 0 plus Ws1 we have already calculated. Ws1 is unknown. So Ws1 remain as it is. Lambda S1 we already calculated. Lambda S1 is nothing but this lambda S1 we have already obtained from the table, that is 2330. If you put it in this equation, we get this equation. WS1 equals to 0.9442 Ws minus 253.4. Similarly, if you make the energy balance over the second effect, now let's make the energy balance over the second effect. So WF minus WS1, again T2 as a reference temperature, WF minus WS1 into I1. So 6000 minus WS1 into 4.1. Now T2 is the reference temperature. So I1 will be CPDT. CPDT will be what? CPDT will be what? T1 minus T2 here, isn't it? So that is nothing but 74 minus 12 plus WS1 is unknown into 2330. That is lambda S1 we have calculated. This right hand side term, this term becomes 0 plus WS2 into IS2 we already know. IS2 is lambda S2 we already know 2470. So that is what we can put it here. So from this equation we get WS2 equals to 0.8404, WS1 plus 617.5. So these two equations we have obtained, and in addition to that, the additional equation is WS1 plus WS2 is equal to 5657. That is what we have calculated here. WS1 plus WS2 equals to 5657. So we have three equations. This equation, this 14 and 13, these are the three equations we are having, and we are having three unknowns, WS1, WS and WS2. So we can calculate these three unknowns. This comes out to be, WS1 comes out to be 2739, WS2 comes out to be 2918, and WS comes out to be 3169. And from these WS1, WS2, WS3, we can calculate areas A1, A2, A3. So WS divided by WS lambda S divided by U1 delta T1 gives me the area 1. So that area 1 comes out to be 75.8 meters square. Similarly, we can calculate area 2. So WS1 into lambda S1 divided by U2 delta T2. That gives me the area equals to 68.6 meters square. So clearly both these areas are significantly different. So these two areas are significantly different because we started with the assumption that the rate of heat transfer is same in both the effect. That's not true, isn't it? That assumption we started because we will get some starting point. But now once we get this area values, now we can redistribute this temperature T1 and T2 such that my area matches. For instance, here, let's say this is 75, this is a higher value, this is lower value. So if I increase delta T1, this A1 is going to decrease, isn't it? Do you agree with me? So here delta T1 I have used as 46. But if I increase this 46 to let's say 48, this area A1 is going to decrease. But if I increase delta T1 with a similar amount, delta T2 is going to decrease because delta T1 plus delta T2, that summation is a constant value 108. So if I increase delta T1 to 48, my delta T2 becomes 60 directly. So that's what we are going to do in iteration number 2. So in iteration number 2, we have redistributed the temperature delta T1 and delta T2 slightly in order to make sure that this area A1 and A2 matches. Isn't it? Remember, both the units are actually the same unit repeated one after another. So their area should match. So this is the checking point. This is the checkpoint. Unless your area matches, you will have to do the trial and error in the design. So we have redistributed the temperature delta T1 and delta T2 as 48 and 60. Now we have calculated based on this new value of delta T1 and delta T2. We have calculated T1. T1 comes out to be now instead of 74 earlier, now we are getting 72. At 72 degrees Celsius, this lambda S1 value is slightly different compared to the previous value. Now the lambda S1 value is 2335. Okay. Now again we have made a balance equation again. So same balance equation we have done. Except that this temperature is now 74 to 72 and this lambda S1 value which is 2330 earlier, now this is 2335. So with this, we got the another equation as WS1 equals to 0.9422 WS minus 231.8. Similarly, we have made the energy balance over the second effect. So everything is same except that this temperature becomes 72 instead of 74 and this lambda S1 becomes 2335 instead of 2330 earlier. And with that, we have got another equation. Now equation number 16, equation number 17, and this original equation WS1 plus WS2 equals to 5657. These three equations are again solved simultaneously to obtain WS1, WS2 and WS. So here we have obtained WS1 equals to 2751 and WS equals to 3166. So A1 is obtained as WS lambda S divided by U1 delta T1. So now my area comes out to be 72.5 meters square, area 1. Similarly, area 2 is calculated as WS1 lambda S1 divided by U2 delta T2 and that comes out to be again 71.4. So if you compare both these areas, these are nearly the same. So we don't need to do one more iteration. So that means the design is acceptable. Whatever the design we are doing here, that design is acceptable. Once we finalize that this design is acceptable, then we can calculate the steam economy. Now what is the steam economy? Steam economy is how much is the total evaporation divided by the steam used. So total evaporation is 5657. divided by the amount of steam used. The amount of steam used is what? WS. So WS is what? 3166. So this total 5657 divided by 3166. If we divide that, we get the steam economy equals to 1.79. So clearly you can see that the steam economy is higher than 1. So multiple effect evaporator gives the steam economy more than 1. In a single effect evaporator, the steam economy approaches to 1. It is not beyond 1. Is it clear to everyone?
Yes, sir.
All right, so this is all about the evaporators. I have one tutorial question to complete, and then your entire syllabus is done. And I am saying sorry to all of you for doing so much thing at the end. But I can assure you that the questions are going to be very easy. Is going to be very easy. If you go through all these lectures, recorded lectures, and the solved examples and the tutorials, you should be able to do it. Of course, this will not be copied as it is, so changes will be there. But if you solve as many problem and as many things which we have done, you should be able to solve the questions. Okay, so let me go back to the tutorial questions quickly, and then we can wind up. Is it okay? So only one tutorial question is there that I will briefly explain you, and then you can yourself solve that. But I will explain the solution, complete solution. I will explain. Just a minute. So I will explain the complete solution of tutorial question. Is it visible to everyone? The tutorial 12 question is visible. Tutorial up to tutorial 11 we have already done in the tutorial classes. Is it visible to everyone? The question?
Yes, sir, visible.
Okay, so now in a tutorial 12, what is been asked? One shell and tube heat exchanger is there. So there is one shell pass and two tube side passes are there in the shell and tube heat exchanger. Steam condenser consists of 3000 brass tubes. So there are total 3000 brass tubes. So again here you can see that one of the fluid is steam which is condensing. So saturated steam is there. Okay. And the diameter of the tube is 20 mm. So cooling water enters the tube. So the steam is flowing through the shell. Steam is flowing through the shell and it is condensing in the shell. Whereas the cooling water, so the water is entering to the tubes at 20 degrees Celsius and coming out at some higher temperature. Okay, with a mean flow rate of 3000 kg per second. The heat transfer coefficient for the condensation on the outer surface of the tubes is heat transfer coefficient is given. So H naught is given. H naught is given as 15,500 at the outer surface of the tubes is given. Outer surface of the tubes on the shell side is given. Okay, but inside the tube is not given. So whatever will be the heat transfer coefficient inside the tube that is not given, that one has to calculate using the Dittus-Boelter equation. If the heat load of the condenser is 2.3 into 10 raised to power 8. That means the Q value is given. Q value is 2.3 into 10 raised to power 8. And the steam condenses at 50 degrees Celsius. So condensing temperature of the steam is given as 50 degrees Celsius. Okay. All right. Now with this we have to calculate the overall temperature of the cooling water. We have to also calculate the overall heat transfer coefficient. We have to calculate the tube length per pass unit using the effectiveness NTU method and the rate of condensation of steam if the latent heat of vaporization is given as 2380 kilojoule per kg. This is what is been given. Again, for a one shell side and n tube side passes, shell and tube heat exchanger, a generalized expression is given like this. Generalized expression for the effectiveness is given as 2 in the bracket 1 plus C plus 1 plus C square raised to the power 0.5 multiplied by 1 plus exponential of minus n 1 minus c 1 plus c square raised to the power 0.5 divided by 1 minus exponential minus n 1 plus c square raised to the power 0.5 and this entire bracket raised to the power minus 1. Here c is nothing but what? C mean by C max. And n is nothing but what? Number of transfer unit that we have already seen earlier, isn't it? Do you all agree?
Yes,
Hello?
sir.
Okay. Now properties of the water are also given at 300 Kelvin. 300 Kelvin, 273 plus. So at 27 degrees Celsius, the properties of the water are given as this. Okay. CPC is 4180, mu is 855 into 10 raised to power minus 6 Newton second per meter square. Thermal conductivity is given 0.613 and Prandtl number is given. Okay. Now the first part in this question is the overall temperature of the cooling water. Now overall temperature of the cooling water we have to calculate. Okay. So overall, so see here the cooling water is flowing through the tube, so we can make the energy balance. So MC CPC delta T will be given as this Q value. Do you agree? Yes or no? So mass of the cooling water multiplied by specific heat of the cooling water and the temperature difference of the cooling water, that should be given as this total Q. And the temperature inlet temperature of the cooling water is given as 20 degrees Celsius, but outlet temperature is not been given, so that we can calculate from this equation. So that is what is been done here. So Q is given here, isn't it? This Q value is given. So this Q equals to MC CPC TCO minus TCI. We can back calculate TCO. Is it clear to everyone? Hello? Does it make sense to everyone? Hello? Is there anyone? Am I audible? Hello? Am I audible? Acha, okay, all right. Okay, so is this this file is visible to everyone which I am showing?
Yes, sir. Yes.
So this Q value comes out to be Q value is given, and from this the outlet temperature of the cooling water we can calculate, that is 38.4 degrees Celsius. Now again in the problem what is been given is the outlet heat transfer coefficient H0 is given, but HI which is inside the tube, that is not given, and that we have to calculate using the Ditters-Boelter equation. So that is what we are doing here. H0 is given, H0 is given, but we have to calculate the inside heat transfer coefficient HI. So for that we are calculating the Reynolds number. So Reynolds number is given by what? 4m divided by pi d mu, isn't it? So based on this we can calculate the Reynolds number inside the tube, So mass flow rate is already given. So that is multiplied here divided by pi d mu. All the properties are also known. We can calculate the Reynolds number. So Reynolds number comes out to be 744.59. Once this Reynolds number is much higher than the 10,000 limit, so clearly since this Reynolds number is higher than 10,000, we can use the Ditters-Boelter equation, that is nothing but 0.023 Reynolds number raised to the power 0.8 into Prandtl number raised to the power 0.4, because we are looking at the heating of the liquid is taking place. Okay, so we can calculate the Nusselt number. Nusselt number comes out to be 367.7, and we can back calculate the heat transfer coefficient HI, that comes out to be 11,270.5 watt per meter square Kelvin. Once we know inside heat transfer coefficient and outside heat transfer coefficient, we can calculate the overall heat transfer coefficient, and overall heat transfer coefficient can be written as this equation: U equals to 1 upon HI by H1 plus 1 by H0. So here we are the resistance offered by the wall of the tube, that we are neglecting, because wall of the tube is made up of metal, and therefore the resistance, conduction resistance offered by that we are neglecting, and we are calculating U as 1 upon 1 by HI plus 1 upon plus 1 by H naught. So overall heat transfer coefficient comes out to be 6527. Is it clear to everyone? Does it make sense?
Yes, sir.
Now we know U we have already calculated. We have already know the area, isn't it? Area also we know because these 3000 brass tubes are there and there are 2 tube side passes are there and the diameter of each tube is known. So we can calculate the heat transfer area. So heat transfer area will be what? Anyone? There are 2 tube side passes. So 2 into how many tubes are there? 3000 into area of the one tube. Area of the one tube will be what? Pi dl, isn't it? Area will be pi dl. So in this case we can calculate the heat transfer, total heat transfer area also we can calculate. Okay. Now another interesting thing to look. The shell side fluid is what? Steam, which is condensing. So when steam is condensing, what will be MHCpH? Remember, in an effectiveness NTU method, you need to calculate CH and CC. CH is nothing but what? MHCpH. And CC is nothing but what? MCCPC. So MCCPC you can calculate because the flow rate of the cooling water that is given, isn't it? That is 3000 kg per second, isn't it? That is given. Correct. This is given. You can also calculate the flow rate into, if you multiply the specific heat, that you can calculate the MCCPC. But what about MHCpH? There is no specific heat when you are condensing. When you are condensing a fluid, there is a latent heat of vaporization, and latent heat of vaporization is the infinite capacity. When you are saying a particular latent heat considered as an infinite capacity. So because of that, MHCpH, which is nothing but Cmax, will be given as infinity. Do you agree with me? This is a very interesting point.
Yes, sir.
So latent, see, there is no specific heat when you are condensing a fluid. There is a latent heat, and latent heat is considered as an infinite capacity. And because of that, MHCpH will be nothing but infinity. So Cmax will be infinity. Cmean will be what? MCCPC. So that is 3000 into 4180. So you get MCCPC equals to 1.254 into 10 raised to power 7 watt per Kelvin. Okay. Now you can calculate Qmax. So Qmax is what? Qmax is given as C mean into delta T, and delta T will be what? Maximum temperature difference present in the heat exchanger. That is what we have said. Remember, when we looked at the heat exchanger, we said that the maximum heat transfer obtained when one of the fluid approaches to the maximum temperature difference, isn't it? And that one of the fluid will be which fluid? The fluid which is having the minimum specific heat multiplied by mass, isn't it? So C mean into THI minus TCI, this is nothing but the maximum temperature difference multiplied by C mean, that gives me a Qmax. So Qmax comes out to be this 1.254 into 10 raised to power 7 into 50 minus 20. What we get is 3.76 into 10 raised to power 8 watt. Now Qmax, Q by Qmax is nothing but epsilon, and Q we already been given in the problem. So problem Q is given as 2.3 into 10 raised to power 8 divided by 3.76 into 10 raised to power 8. We get the effectiveness value, and effectiveness value comes out to be 0.61. Also, C mean by C max is what? C mean is this value divided by C max is infinity. So any number divided by infinity is 0. So capital C is 0, isn't it? So in this equation, this is the equation given for 1 to n pass heat exchanger. So in this equation, we can put this capital C equals to 0, and we can put this epsilon equals to 0.61, and we can back calculate the value of n. And if we do the rearrangement and calculate the value of n, which is nothing but the effectiveness comes out to be 0.94. So effectiveness comes out to be 0.94. Okay. Once we get the effectiveness value of 0.94, effectiveness is defined as what? UA by C mean. UA by C mean is nothing but NTU or N, isn't it? So now U we have already calculated, isn't it? C mean we already know. C mean we already know, isn't it? We can calculate the calculate the area. So area comes out to be 1805 meter square, isn't it? Clear? Now this area which is we have calculated, area will be equals to what? Number of tubes multiplied by number of tubes is this N. This is a small n, sorry. This I have made it capital N, but this is not capital N. This is a small n multiplied by number of passes. How many number of passes are there? 2 multiplied by area of one tube. Area of one tube is what? Pi dl. So everything is known in this equation except this L, capital L. So we can calculate this capital L as A divided by N into 2 into pi d. That comes out to be 4.84. So length of the tube, length of this tube comes out to be 4.84. Also in the last part we wanted to find out the steam condensed per second. So ms, that is the steam condensed per second multiplied by latent heat of vaporization, is given as Q. So we can rearrange this equation and we can calculate ms. So ms is nothing but Q by LV. So that comes around 97 kg per second. That is the answer for the last part. Is it clear to everyone? Hello?
Yes, sir. Clear.
Okay, so I am not going to do the last tutorial. Tutorial number 13 is also similar to the problem which we have solved in the class today. The only difference here is you have to follow the same procedure. You have to note everything here in this figure first, and then you have to make the you have to calculate the delta T1 and delta T2 assuming the same rate of heat transfer, isn't it? Then you find out the T1, calculate lambda S1, and then corresponding to lambda S1 you calculate the latent heat of vaporization, isn't it? Then make a balance, you get this equation. Similarly for the second effect you make the balance, you get the second effect, isn't it? Use the average value of Cp in this case, and then from this you can calculate area 1, area 2, and both these areas are different. And therefore you go for a second iteration. In the second iteration you rearrange this delta T1 and delta T2 and again do the calculation, and here you can see that the areas are matching. So see, this question is nearly the same as the question which we have solved today. So can you do it yourself? Is it clear?
Yes, sir.
So I will just keep it this as it is for a while, so that if you wanted to see the solution, you can get the solution on the in the video itself. Okay, so this is you have to first mark all the variables and correspondingly then you solve it. Then this part. Then this part, and finally you solve for the second case. All right, so let us stop here. I'm sorry for but I thought it is better to complete the syllabus, at least the evaporator, because many of you might be writing the GATE examination. So your syllabus up to evaporator is there in the GATE examination. That is why I completed this evaporator part at the end, even though we could have, I could have eliminated that part because this is a curtailed semester and we are getting only 28 lectures and not complete 43 lectures. But I thought it is better to complete the entire syllabus, and I will give you a simple, questions. But you should not feel that something is left out. Okay. All right. So again, I would like to thank all of you to hear me out throughout this semester. And if I have, at any time, if I have somehow not able to explain you something or anything, please forgive me. I have tried my best to explain everything, whatever I had. And thank you for, listening me patiently, and particularly those who are attending the classes regularly. So do you wanted to add anything? This is the last class.
Sir, do the 7 to 13 will be uploaded?
Please repeat.
The solution will be uploaded
So
or not?
anyway, this solution I have discussed in this video. Na? It is already there in the video. And this video will be available, isn't it?
Yes, sir, but it is more easily accessible in case we have to point out our mistakes in a couple of.
So use this video and write down these solutions yourself. Anyway, tutorial the students has to solve. Na? I am solving it. That's another story. But the student should solve. So you solve this solution again, tutorial number 12 and tutorial number 13, isn't it? And note down the solutions in your copy, isn't it? Then you will get most of the things.
Sir, I was just asking just to so like we wanted to confirm the answers or maybe missing some steps. So it would.
So I have shown all the answers. That's what I'm saying.
Yeah,
I have
yeah,
shown all the answers.
Yes, sir, I got it.
I have shown all the answers. I have not eliminated anything. The entire thing, except that instead of doing it on the whiteboard, I have shown in the directly on that, isn't it? Does it make sense, Prakhar?
Yes, sir, it's fine. It's fine. No problem.
Okay, all right. Why I am reluctant? Because then, these are circulated. Isn't it? These are circulated across the batches. For your batch, I can give, there is no problem, but then it's circulated to the next batch also. Isn't it? I want them to work, isn't it? In this semester was curtailed. That's why we have to do it. But otherwise we do it by hand calculation, isn't it? Every time. That is the only reason I am in general reluctant to give you the printed solution. I want you to write. If you write it, make it in your in your notebook or something. It's perfectly all right. It's perfectly all right. Okay, that is allowed. But giving something which is printed, that in a way sometimes makes people not to work, particularly in the next batch. All right. Hello.
Yes, sir. Yes.
So thank you everyone, and I'm sorry if I have sometimes if something is not if I'm not able to explain something, or if you are not happy with something, I'm really sorry. I have tried my best to deliver everything what is mandated in this course. Again, I'm repeatedly saying the question paper will be very easy. Today I'm going to send all your quiz 1 and minor 1 marks. So please see if there is any discrepancy, please let me know. And we are having a quiz on the last quiz on the Sunday. So on Monday I will show you your quiz 2 copies also. So Sunday will be the examination, and Monday you will get all your quiz 2 copies.
But sir, from Tuesday we have examination, so sir, that would be like.
So that's why I'm showing on Monday itself, isn't it? So I'm showing you everything before the your major examination.
Sir, can you show like I guess after.
No, after why I'm not putting it after, because then you can prepare yourself based on whatever the PMT you get. Okay. Pre-major total I wanted you to get before your major exam starts. So Monday you will get all your marks, and again I'm going to show you your copies from 2 o'clock onward, 2 to 4 the same time. If you have a time, you come. If you do not have a time, anyway I am going to post all your PMT marks Monday evening. If you don't wanted to check your copies on that day, it's okay, but I will show on that day. And I in general want students to check all their marks before the major examination, because then it becomes clear So pre-major total becomes clear before the final exam. So Monday you all will get your copies back, your marks and everything on Monday. Today I am going to send your quiz 1 and minor 1 marks. If you have any discrepancy, you clarify it on Monday. Okay.
Thank you, sir.
All right. Thank you so much. Let's wind up.
Thank you, sir.
Thank you so much.
Thank you, sir.
Okay. See you guys. Best of luck to everyone. Take care.
Sir, we enjoyed the lectures. It was very nice.
Thank you.